Alright, new topic. Let's talk about Bitwise Operators and Bitwise Operations. I am going to have to make an executive decision because of all the holidays we had during this semester, and we're not going to talk about programming paradigms. I am sorry. You can read ahead in these slides, though. I just won't have time to get to them in order to get to everything we need to get to. Okay? So that is quite sad, but at least we're going to learn about Bitwise Operators right now. So let's get started with those. So you might be wondering, what does that even mean? But there is the word bit in the title, so that is the hint. We are going to be working with binary numbers, essentially, and we're going to be working with individual bits of binary numbers. Like, how do I figure out that this bit is a 0 or that it's a 1? And how do I change it? So that's what we would like to do. Okay? So in order to talk about bitwise operators, things that work on individual bits of a number, we have to talk about numbers again. So let's remember what numbers are all about. So let's do that because, yeah, bitwise operators, they work on the bits of a binary number. Remember that a bit is just a 0 or a 1. A binary digit, that's what it's short for. And so how do we remember what our numbers are, right? It is like this. So if you have 1, 0, 0, 1, 1 in binary, and you want to convert that to decimal, remember how to do that? It's always, you start with this one. This is the 2 to the 0's place. It's 1 times 2 to the 0, plus 1 times 2 to the 1, plus 0 times 2 to the 3, plus 0 times 2 to the 2, plus 0 times 2 to the 3, plus 1 times 2 to the 4. And that's how you convert. Yeah. Another example, like what's 1, 0, 1, 1 in base 2? That is 1 times 2 to the 0 plus another 1 times 2 to the 1 plus 0 times 2 squared. So that contributes nothing. And then 1 times 2 cubed. And the final answer there is going to be 8 plus 2 plus 1, which is 11. And that's what that means in base 10. So that's binary conversion all over again. And, okay, 0 in binary is just 0, right? It's all the same, but we're going to be talking about like integers which have a certain size. The number 0 is just a bunch of zeros. You can put 0 at the front of 0 and it's still 0. Okay, so 0 in our number system is just still a bunch of zeros, and that's going to be important later. And then finally, we have only been talking about binary, like 1, 0, 1, 1, right? Everything in our computer is made up of binary, but I've only been telling you how to create positive numbers in binary, haven't I? I've never told you how we represent, because it has to be in terms of 1s and 0s, because everything is 1s and 0s in a computer. I haven't told you how to represent negative numbers, negative ints, for example. So let's figure that out. Int, the type int, right? It is able to hold negative numbers. Like, I can set an int variable to -1 if I wanted to. We need to figure out how it's doing that. I need to show you that. The very most important thing about this, before I talk about negative numbers, is remember how many bits certain types are, how wide they are. So int, for example, every integer is 32 bits long exactly. If you want to store the integer 0, you're going to store 32 zeros in the int 0. Okay? You're going to store exactly 32 zeros. And that's going to be important for negativity now. So with that in mind, let's figure out what -1 should be. Okay? We can figure out what number it should have been based on what we know how to do with binary numbers. So here's the idea. Whatever -31 in 32 bits of a binary number is, because it needs to be 32 bits long to be an int, right? Whatever -1 is, well, adding it to 1 better make 0, right? Because that's what it means to be -1. So let's figure this out. All right? We're going to notice that -1 in binary ends up being all 1s. Crazy. Okay? So let me show this to you. Let's pretend that our numbers are 4 bits. Okay? Instead of ints, instead of working with ints, let's pretend that we're working with 4-bit numbers. So the biggest our number could be, like the smallest number is 0, 0, 0, 0. Our biggest number is 1, 1, 1, 1. Okay? And our job is to figure out, for these numbers, these tiny ints, let's say, what in the world is -1? And the trick is, well, it's the number that when added to normal 1, this is normal binary 1, right? We end up with all zeros. That's what we want to get back, right? So we have to figure out what to put here. What should -1 be? So here is the idea. I need to get a 0 here, right? So I can't put a 0 here. The rightmost bit of -1, whatever it is, it's not 0 because 0 plus 1 in binary is 1. And I need that to be a 0 here. So I'm forced to put a 1 here. Does that make sense? Because otherwise, if I put a 0 here, the answer is 1 in this bit. I need 0 out. I need to find what -1 should be, and -1 should give me back all zeros when I add it to just +1. So this better be a 1. And that's going to force me to carry, right? 1 plus 1 is 1, 0 in binary, so I'm forced to carry. That's what's going to happen here. And then, okay, I need this to add all together to make 0. I have a 1 sitting here from the carry. So I can't put a 0 here again in this bit because I want the answer to be all zeros, right? Which again forces me to put a 1 here in the next bit of -1. And that'll put a 0 here. Again, it will carry and force me to put another 1 here. Again, that will carry, force me to put another 1 here. And then again, that will carry a 1 outwards, but I just told you that our numbers are only 4 bits long. We don't have room for that carried 1. And so the answer is 0, and that means 1, 1, 1, 1 is -1 for a 4-bit number. Does that make sense? That's the idea. We take advantage of the idea that that final carry out into the 4th bit. This is like the 0th bit, the 1st bit, 2nd, 3rd bit. This is the carry into the 4th bit, let's say. Really, bit number 5, I guess. That does nothing because we don't have room to put it anywhere. We don't have 5-bit numbers, we have 4. We can't add an extra bit to our numbers. And so that is why this works. That's why we can store negative numbers just like this. Okay? And so you can imagine that for 32-bit numbers, it's 32 ones all in a row. That's -1. 1, 1, 1, 1, 1, 1, 1, dot, 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 1, 1, 1, 32 of these. For the int -1. Let me draw that a bit cleaner. For the int -1. Okay? That's the idea. That's what's happening. And we can do the same thing to figure out what -2 should be for a 4-bit number. What should -2 be? Well, it's the number that when added to +2, we end up with 0. Okay? So what needs to go here? I need to end up with 0 here, so I can't put a 1 here. Now I'm putting a 0. Okay? And then I need a 0 here. I already have a 1, so I can't put a 0 because that would make a 1. Whatever -2 is, it should add into 2 and make all zeros. So this needs to be a 0, which forces this to be a 1, which forces me to carry, which forces this to be a 1, which forces me to carry, which forces this to be a 1, and we have that carry out business all over again. And so it looks like -2 is 1, 1, 1, 0. Does that make sense? It's the number that when added to +2 makes 0. And so for 4-bit numbers, it's 3 ones and a 0. That's how that works. Okay? And this seems tedious. Like, how do I discover the negative numbers? I have to like do a binary addition. That seems horrible. You can do this a bit faster. There is a pattern. Okay? Our negative numbers are stored in what's called 2's complement form. Okay? And so in order to negate a number, to make it from negative to positive or from positive to negative, all you have to do is flip all of its bits, change all the 1s to 0s and all the 0s to 1s, and then add 1. So let me show you how to do that. So let's start with, let's start with the number 1 for 4 bits, let's say, and let's calculate its negative. Let's calculate -1. Let's put it into 2's complement. So we flip all the bits and we add 1. So flipping all the bits is changing all the 0s to 1s and all the 1s to 0s. And then we're not quite done. We still add 1. And that'll go there. And so that's our -1. Okay? So that's the pattern. That works for any number. It also goes in reverse. So we started with 1, 1, 1, 1, that's -1. If we want to negate that back to the positive version, we can do the process over again. We negate it by flipping all its bits and then adding 1. So 0, 0, 0, 0, that's flipping all the bits. And then adding 1 gives me 0, 0, 0, 1. And so -1 to +1 to -1, and it works for any number that you want to negate. That is 2's complement, okay? And that is quite nice and quite powerful. All right, so now I'm ready to teach you about Bitwise Operations. Because when working with numbers, like I have an int, I have 32 1s and 0s to use, don't I? I can have 1, 0, 1, 1, I can have 32 bits to store stuff, and sometimes instead of storing just one giant number, it's nice to store other things than numbers inside of our ints. Like, for example, with an integer, you have 32 1s and 0s, and what is a 1 and 0 but a Boolean value, like a true or false? So you can store 32 Boolean values then inside of an int. And that actually saves you a lot of space. Like maybe this bit is part of your video game program, and if this bit is a 1, it means you have an extra life. If it's a 0, it means you don't. And like maybe this bit means like the character is riding a horse right now. You can pack a lot of information, doesn't have to be a number, into a single integer by accessing each individual bit, and that's quite nice. Okay, so there then need to be ways to work with those individual bits. Okay, and I'm going to teach you one of those ways. Like, how in the world do I get that 12th bit? How do I set the 3rd bit? Things like that. So let me show you one of those ways that is called Bitwise AND. Bitwise AND lets you perform Boolean AND, which you already know. It lets you perform Boolean AND on each bit of a number. All right? And remember that 1 is going to be true and 0 is going to be false. So let me show this to you. Bitwise AND works like this. And sadly, it uses the ampersand. So I'm so sorry. There are now 3 things that you know about in C++ that all use the ampersand, depending on how you use it. It's either the address of, or reference, or bitwise AND. That's very unfortunate. I'm very sorry about that. But that is just the breaks. So here is an example of bitwise AND. Let me say that I'm working with 4-bit numbers again, 1, 0, 1, 1, and 0, 1, 1, 0. And I want to perform bitwise AND. It takes 2 numbers, I AND them together, we say, and what happens is it performs Boolean AND on each of those bits inside of these 2 numbers. And here's what happens. What it does is it lines them up. It looks at this, looks like this is a 1, this is a 0, and it ANDs them together. It's true ANDed with false, because 1 is true and 0 is false. And so the answer is false, because anything ANDed with false is false. And then it goes to the next bit. And it calculates a new number this way. So it looks at these, and it performs Boolean AND on them. True and true. Oh yeah, that's still true. So that's a 1. False and true. False. True and false. Darn, that's false again. So the answer is 0, 0, 1, 0. It's 2, I guess. And so in code, you would probably write this as normal numbers, right? Normal integers. So you'd say like 11, base 10. Bitwise ANDed with, this is 4 plus 2, this is 6. This is 8 plus 3, so 11. And this is 6. That becomes 2 somehow. That's what bitwise AND is doing. So it makes not a lot of sense with the numbers, but it makes more sense with the bits. And remember, what's happening is it's doing the Boolean AND operation. So this 1 and 0 is equivalent to trying to do true and false. And the answer is, of course, false. Okay, so that's what is going on here with bitwise AND. So let me show this to you in code. So So I can see out the result of performing bitwise AND on 11 and 6. It's just a single ampersand, and the answer we have calculated should be 2. Yay! So we did that. All right, so that's the ampersand operator. Sorry, there's another thing for it, another thing that it's used for. And bitwise AND is good for extracting bits. It's good for figuring out, like, was this bit a 0? Was it a 1? Let me show you how. Let's say we have this this binary number, 1011. That's the number we start with. And we'd like to extract this bit. Let's call that the third bit. Let's say that bits start like this. This is bit 0, this is bit 1, this is bit 2, this is bit 3. And I want to extract the value of this third bit. Is it a 1 or is it a 0? Here's how you can use bitwise AND for that. What you do is you AND with the special number that's only 1 in this position and false everywhere else, 0 everywhere else. I'm having a lot of trouble drawing an ampersand that looks nice. There we go. So what you do is you AND with this special number where only the third bit is set. And once you do that, I think you can see that this is going to force, like these zeros here is going to force all these numbers to become zeros, because when you AND, if there's ever one 0, it makes it all 0. The result is 0. And then, depending on whether this bit was true or false, there will either be a 1 here or a 0 here. Isn't that nice? And so we'll pick out that 1, and it'll be a non-zero value. That's the trick. So we just performed 11 ANDed with 8, and that just got us, that was 11, and this is 8. Just a 1 right there. That's 2 to the 3. 11 ANDed with 8. That gives me just 8 back, because it was set. Does that make sense? That's how it works. So I can give you that one as well. Oops, I wanted this. 11 ANDed with 8. This is non-zero, so the bit was, so bit 3 was set. For example, if I wanted the other bit, some other bit, if I wanted to know if bit 2 of this number was set, I would AND with 100, which is the number 4. This is 0, so bit 2 was not set. That's what's going to happen. So darn, it wasn't set in that location, and so ANDing with 4, which is the number where this bit was set, that's like 4 is 0, 1, 0, 0. It would extract this bit, and darn, it wasn't set, so the whole thing's 0 still. So bitwise AND is good for extracting bits. That's quite nice. And just like we have Boolean operations we know about AND, there's also OR, of course. So let's talk about that too. So just like how bitwise AND ANDs together every bit individually, bitwise OR ORs together every bit individually. And the OR operator is like just how this one was Boolean AND was 2 ampersands. We chopped off one of those to make bitwise AND. Just like Boolean OR is 2 pipes, we chop off one of those pipes and we make just a single one. Okay? That's what happens. And so bitwise OR ORs together every bit. Here's how it works. So let me give an example of bitwise OR. So I'm going to take these two numbers, 1011 and 1100, and I want to OR them together, the bitwise OR. And so it's going to work on every individual bit at once and OR them together. So like for this one, it'll see true and false, and it needs to OR those. So it's going to calculate what is true ORed with false. And remembering our truth tables, the answer is true, right? So the answer here is 1. Same for this one. It's going to be a 1. Actually, let me make this a bit more interesting. Let's put this as a 0. So now this answer is 0 here. Let me go back to green so it's consistent. So this is 0 because false ORed with false is still false. This is a 1 because there's a true, and this is a 1 because there's 2 trues. So that's the final answer, 1101. So what we were calculating there was apparently, again, it doesn't really make sense when you go to numbers, but it was, this is 9 base 10, ORed with, this was 8 plus 4, so 12 base 10. Gives back, what in the world is this? 12, 13. 13 base 10. Crazy. So let me show you that. 9 ORed with 12. So a single pipe character that does bitwise OR. And we get our 13. Yay. Alright. That is fun. And yeah, remember that OR gives back true whenever one-sided was true. It doesn't take a lot for OR to give back true. And bitwise OR, just like bitwise AND, it was good for something. It was good for extracting a bit of a number. Bitwise OR is good for setting a bit of a number. Okay? So let's pretend we wanted to do that. We wanted to set a certain bit. So here is a number that I'd like to set a bit out of. And so the bits are numbered like this. This is bit 0. Oops. This is bit 1. This is bit 2. This is bit 3. I would like to OR this with a special number so that I set. Like I want to set this bit, for example, from a 0 to a 1. I want to end up with 1011. And here's how you do it. Here's the special number you OR with. You just OR with all zeros everywhere you don't want to set, and OR with a 1 the place you do want to set. So this is the number with the 0th bit set. And that'll force, when you OR them together, of course, it'll take what we had before, because zeros don't affect when you're doing OR, and then it'll make sure that this one is finally a 1, if it wasn't already. You see that? That's what you do. And so this is kind of doing 8 plus 4, or 8 plus 2, that's 10, ORed with the number 1, gives you 11, surprisingly. So that kind of looks like addition, but it's not really the same. Okay? So that's how that works. So to set a bit, I started with 10, I ORed with 1, now the 0th bit is set. And so that gives me 11, a number with the 0th bit set, starting from 10, starting from my 1010. So that's how you do it. And let's keep going, because there's more than just AND and OR, right? What else is there? There is a NOT, so let's do bitwise NOT. All right. So our bitwise, our normal logical NOT was the exclamation point, right? There's not like 2 characters here, so we kind of have to use something else. The bitwise NOT character, NOT operation, is the tilde. Okay. That's what we use instead. So bitwise NOT, it takes a single thing, takes a single number, and it flips all the bits. So everything that was true becomes false. Everything that's false, that goes and becomes true. Okay, that's the idea. So bitwise NOT flips all the bits of a number, and it looks like this. It's just a tilde. All right. So for example, if I use tilde, bitwise NOT of 1001, that will transform this number from what it used to be into, well, 1 becomes a 0, 0 becomes a 1, 0 becomes a 1, 1 becomes a 0. So it makes this number. So apparently NOT of 9 for 4-bit numbers at least. This is very important that I say that, because there might be a bunch of zeros over here that might be 1s for a 32-bit 9. So this is like a 4-bit 9. That becomes apparently 6. That's what's going on there. Okay, so that is what bitwise NOT looks like, but it's not quite the same for 32-bit numbers. Let me show that to you. It doesn't give you 6 back. There, not 9, right? The answer is -10. Because of the way that negation works. It's very close to being a negative number. That is exactly -9. So the tilde flips all the bits, and C++ remembers that, and it thinks that it's a negative number once you do that. So that should make more sense once I make this function. But it looks like I have reminded myself to use a makefile for today. Even though I'm just using a single program right now, it's going to give us some nice examples. So good practice to make a makefile for this, even though we have one file to compile. All right, so let's make a makefile to compile my bitwise.cpp into just a single executable called bitwise. So that's what I've been doing here when I use G++. So let's take this and put it into a rule, a makefile rule. So I want something called bitwise. That's my target. It requires bitwise.cpp. We could alternatively go through the .o file, but it's just a single file. There's no real need for that. And here's what you do based on your bitwise.cpp to recompile it to make bitwise itself. Okay? So that's a good practice with our make files. And so instead of saying G++, now I can just say make bitwise to recompile. Or, because it's the first rule, I can just say make. And it'll run the bitwise rule because it's the first rule in the file. Isn't that cool? So that is a makefile, now that I've remembered it. Back to our programming. So let's make a negate 2's complement function. Negate a number by doing the 2's complement operation on it. Let me show this to you. And I'd like to call, for example, cout negate 2's complement on the number 9 and have it give back -9. So takes an int, gives back an int. This function negates. I think I was supposed to use the name that I said here, just to keep it all consistent. Let's call it this. So let's do boop, boop, just like that. Negate 2's complement, and then instead of this one, I'll say it this way. There. Now I'm happy. So this function negates x, so returns -x in a special way by doing the, by performing, or creating, let's say, the 2's complement. So what does it mean to negate a number really? Boop, boop, boop. To negate a number, flip all its bits and then add 1. Do you remember how to flip all the bits of a number? What is that but bitwise not? Oh man, oh man. So flip all the bits and add 1. So return, flip all the bits of x, and then add 1 to it, and that makes the negative version of that number. That's how we store negatives. We just spelled it out. That's really what C++ is doing for you when you say -x. Isn't that cute? So make bitwise, or just make, and it recompiles it. And what do you know? We went from 9 to -9. And this works both ways. We can go from -9 to 9. Boop. That's beautiful. That's really how negation is working inside of our computers. And so now you know why -9 gives back -10, because it's almost the 2's complement. You just had to add 1 and you get the negative version. So hopefully that spells it all out and makes at least a little bit of sense. This is definitely a weird thing to want to do, to extract the individual bits of a number and to do stuff with them, but hopefully you're getting the hang of it slowly. Please yell at me if you have any questions about this stuff. Alright, now I have a question for you. I think I've given you enough to think about. Let me make sure this is all settling in your brain. So please try to write code that unsets the 5th bit of an int named x. So you maybe make a function, call it unset 5th bit or something. You take an int x and you set that bit to a 0 no matter what. So remember the order. Like, let's pretend that this is the number that you would like to set the bit of, or unset the bit of. 111011011. You'd like to change maybe the 5th bit, right? So this is bit 0, 1, 2, 3, 4, 5. Remember that they start at 0. So this is bit 5, and you would like to unset it. So you'd like to take this and make it 0 no matter what. Even if it wasn't already 0, you're going to make it 0. And then the rest of the number stays the same. So it's 1, 1 still, 0, 1, 0, 1, 1. It's just this got changed to a 0. And it looks like I didn't do very well at keeping these in the same spot. Sorry. This is the number. Well, I didn't want to do that. This is the new number. Okay? That's the idea. That got changed from 1s to a 0. Good old PowerPoint, not very helpful today. There we go. So that's the new number. We unset that bit. See if you can write that in code. And my hint for you is you can do it with a not and an and my extra hint for you is that you should try to extract every bit, because that's what and is good for, except bit 5. How would you do that? Maybe with a not involved. Okay, so give that a try, and then we'll talk about it. So here's the secret. You start with this number 111, 01011. We would like to create the number 110, right? 01011, because we want to unset this bit no matter what it is. And I claim that the easiest way to do that is with an AND operation, with this special number, with let's see, this one needs to be a 0 for sure. And then all these can be 1s. Do you see how this is a nice special number where everything but bit 5 is set? Everything but bit 5 is set. How might you create that? The easiest way is with not. Did you notice that? So how do I make a number where only bit 5 is unset? Well, start with the number 000, 32 bits wide, on and on and on forever until you get here. This is a number that is 0, 1, 2, 3, 4, 5. This is the number where only bit 5 is set, right? If you were to negate this number with bitwise not, that's what I mean by negation here, you'd end up with exactly this number, with 1s everywhere but bit 5, because you're flipping every bit. You see that? That's the trick. That's what you can do. And this is apparently the number 2 to the 5. So 1, 2, 4, 8, 16, 32. It's the number 32, the number with just a 1 in bit 5. So you need to calculate tilde 32 to make this special number to AND with, and that will get rid of it. It will get rid of that piece. So you say, you start with your number, int x equals whatever, and here's how you unset the 5th bit of that x. So you say x equals, well, it equals what it used to be, right? You start with it as usual, and then you AND that with this special number with just bit 5 unset. I'm going to pick out, you're extracting every bit, right? And that's what 1s do, they extract bits. You're extracting every bit except for bit 5. So ANDed with bitwise not of 32. And that'll do it. That'll change x to be whatever it was before, but it makes sure that bit 5 was unset. All right? That's a fun little example. Did you get it? And that's the idea. So I have a couple more things to show you about Bitwise Operations, and that'll be it for the day. So the next one is called Bitwise Xor, or exclusive OR. And this is a different kind of operation. So XOR, it's short for what's called exclusive OR. And let's compare with our regular OR that we know and love. All right, so our regular OR operator looks like this. Think of this as your Boolean OR, right? So if you have two Boolean variables, you can do x ORed with y, and I'll just use English for now. So if x was true and y was true, then x or y is true, and then I can show you all the other options as well. So this is what the truth table for OR looks like, right? It's always true unless both of them were false. So that's regular OR. let me show you exclusive OR now. It looks like this. X and Y, and then X XORed with Y. Here's the result. It looks almost like ORs. This is false still, this is true still, this is true still, but this one right here, instead of being true, it happens to be false. So this is the main difference here. That's the one that changes. True XORed with true is not true, it is false. So this is called exclusive OR. It's true when just one of them is true, but not both. It's exclusive. They can't both be true. So regular OR gives back true when one or both sides are true. Exclusive OR only gives back true if only one of the sides is true. And so really, our regular OR is also known as inclusive OR. It likes to share. Exclusive OR does not like to share. Okay? It's only true if exactly one of the sides is true. And the Bitwise Xor operator is the caret. And this is why, as you were starting to learn C++, maybe you accidentally typed this and expected it to be the power of operator, and you got back some weird answer. That's because it was doing exclusive OR, and you didn't understand it yet. All right? So this is how exclusive OR works. If you do 0 exclusive OR with 0, that gives you back just 0. And then, let's see here. If you do 1 exclusive OR with 0, that gives you back 1. All right? And I'm going to come back to these. I'm going to redraw this, actually, because it's going to be a kind of cool thing to notice. So 1, 0, 1, 1. Let me give you an example. XORed with 0, 1, 0, 1 gives back the number what? Well, 1 exclusive ORed with 1, oh man, that's a 0. 1 exclusive OR with 0, that's a 1, that's a 1, and that's a 1. Okay, that's supposed to be 0. And so it looks like this is 11, 8, 9, 10, 11. Exclusive ORed with 5. That gives you back 8 plus 4 plus 2, so 14. So that's what's happening. All right, that's exclusive OR. So that's definitely not to the power of, right? So that's what it's really doing. So exclusive OR. And one good thing that exclusive OR is for is addition. Actually, inside of your computer, you have a bunch of circuits performing exclusive OR because it's almost addition. You just have to do a few extra things to get there. Let me show that to you. So 0, instead of true and false, let's use 0 and 1. 0 exclusive ORed with 0, that's 0. That's the same as plus for a single bit. 0 exclusive ORed with 1, that's 1. That's the same as plus. What? 1 exclusive ORed with 0 is 1. That's the same as plus for a single bit. 1 exclusive OR with 1, that's 0, which is the same as plus for a single bit because we have to carry. Isn't that so cool? So exclusive OR is kind of doing addition, and you can make it do addition inside of a CPU. When you take CSCI 45, if you get there, then we'll talk about this in a lot more depth. But that is your sneak peek. So Bitwise OR is good for some things. That's one of them. The final piece of the puzzle is shifting. This is going to make our lives so much easier. All right. So Bitwise shifting looks like this. These are the operators. Actually, C++ stole this operator for cout, and it stole this one for cin. These originally were shifting operators from the C language. So left shift and right shift, they work pretty darn logically. So here's a number, 1011 base 2. If I left shift that by 2, left shift it by 2 bits, we say, what it does is it just moves this number to the left. It adds zeros at the end. So this becomes, it turns it into 1, 0, 1, 1, but it shifted it left, so it made some room for 2 new zeros. That's all. That's what's happening. So this was, gosh, what number is this? This is 11 base 10, shifted left by 2. That became, what is this number? This is the 1's, the 2's, the 4's place, the 8's place, the 16's place, the 32's place. So 32 plus 8 plus 4, that's 44. Base 10. And so it looks like it turned 11 into 44. All right? That's what happened there. So that's left shift. What is that really doing? It's secretly multiplying. Left shifting is another way to multiply. So 0, 0, 1, 1, if I left shift that by just 1 bit, that brings in room for, it makes 0, 0, 1, 1, 0, right? It makes a new room for another 0 there. And it turns this number, which was 3, right? It turned 3 into 6. It multiplied it by 2. Isn't that neat? So it's multiplying by powers of 2 when you shift. This was 3 times 2 to the 1. This was 11 times 2 to the 2, because I'm shifting by 2 bits. That's what it calculates for you. Left shift is another way to multiply by powers of 2. And right shift is another way to divide, essentially, by powers of 2. Let me show this to you. So right shift just does the opposite. If I would like to right shift a number, if it looked like this, 0, 0, 0, 0, and then we had like 1, 0, 1, if I right shifted that by 1 bit, that turns into just, well, it has no more room left for this one because we're moving it away. We're shifting in a 0 maybe over here, but we're getting rid of this bit over here, shifting them, just like that. Then this turns it into like 0, 0, 0, 1, 0. Okay, got rid of this bit. That's what's happening. And it brought in like a new 0 over here. And so it turned, what is this? 1, 2, 4, 5. It turned 5 into 2. And that's what it's doing. It's dividing by a power of 2. 5 divided by 2 to the 1, because I'm right shifting by 1. It turns it into just the number 2. It's integer division. Okay? So let me show that to you, all this shifting stuff. So I had 11, left shift 2. I had 3, left shift by 1. And I had 5, right shift by 1. And so this divides by 2 squared. This multiplies by 2 squared. This multiplies by 2 to the 1. And this divides by 2 to the 1. Just 2. And it all has to do with this number. 2 to the what? 2 to the 1, 2 to the 1, 2 to the 2. That's how the shifting works. It either adds some zeros or gets rid of zeros, usually. 44, 6, and 2. Okay? So that's what shifts are good for. And let's see, what else do I want to say? Right shift is kind of weird. Let me just tell you that now. It works differently for normal ints, which have negative numbers, and unsigned ints, which do not have negatives. When you do a right shift on a normal int, it brings in whatever was there, right? If the number was negative, it brings in a 1 because we want to kind of keep it negative. I won't talk. I'm not going to test you on this. I won't get too far into it. Look into it in your book if you're interested. But right shift on ints brings in a 1 if it's negative and a 0 if it's positive. So if this were really a negative number, it wouldn't have added a 0 here. It would have brought in a 1. Because that's what negative numbers look like. And then finally, right shift on unsigned ints, which can never be negative. It always brings in a 0. It always makes it smaller. Okay? And so that one really divides by powers of 2. That's what's going on there. All right, so that's bitwise shifting, and here's like the pattern. If you do n left shift by some amount I, that gives you back n times 2 to the I. All right? And a similar thing is true for right shift. All right? And shifting, in addition to being another way to multiply and divide, is also a really good way to get and set bits. This is going to make your life so much easier, because I used to have to remember, okay, if I want to get bit number 3, I better create the number 8. That's no fun to have to remember that. I can use shifting to make that number for me very easily. Okay? So for example, if I want to set the third bit of a number, I can just OR by 1 left shifted by 3, can't I? Because, like, here's my number, 0, 0, 1, 1. I want to set the third bit, which is this one. Then I can just, I need to OR by this number, right? 1, 0, 0, 0 to make my answer that I want back. But what is this? What is that but 1 left shifted by 3? So you started with 1, and then you left shifted, so you made some room. Over here, you brought in 3 zeros. Isn't that nice? So that makes a number with just that bit set, with just bit 3 set. And so same thing works for AND. If you want to get the third bit of a number, you AND by 1 left shift 3. So here's my number that I want the third bit of. It happens to be a 0. And I would like to AND by this to see if it was 0 or not. But what is this? But, again, 1 left shifted by 3. And so that gives me back 0 to know that, oh yeah, that wasn't set. Isn't that cool? So yeah, shifting is great so that you don't have to remember. So let me redo our AND operation, for example. That's so much easier. It's easier to see, like, oh yeah, I want to do something with the third bit now. Yay. So that's beautiful. And then that is, I think, everything that I wanted to teach you that was new. The last thing I want is for you to try one last thing. So here is my challenge for you. See if you can write code that not sets always, not unsets always, but code that toggles the fourth bit of an int. And let's say that that int is named x. Okay? So it should set that bit to a 0 if it were a 1, and it should set it to a 1 if it's a 0. So for example, here's a number, 1, 0, 1, 0, 1, 0, let's say. So that's my number. This is bit 0, 1, 2, 3, 4, 5. So here is bit 4. I would like you to toggle it. So your process should take this number and make the 0, 1. It should make 1, 1, 1, 0, 1, 0. And then if you did that same process on this new number, it should go back to this fourth bit and reset it to be a 0 now. 1, 0, 1, 0, 1, 0. Okay? Can you do that? I also claim it's possible to be done in a single line of code. All right? So you start with your number, then you do something to it. X equals something, and that will toggle bit number 4. Okay? So give that a try. And let me now show you the answer. So let me use a different color. So here's my number, 1, 0, 1, 0, 1, 0. And let me show you that you can, let me make it smaller actually, 1, 0, 1, 0, 1, 0. I want to toggle this bit. Let me show you that you can use exclusive OR to do this. That's one thing that exclusive OR is good for. It's good for toggling bits, making 1 zeros and 0s 1s. Here's what happens if I exclusive OR this number by the number where just this bit is set. So I get everything that used to be there, because exclusive OR by zeros, if there's a 1, it makes the answer 1. If there's a 0, the answer is 0. But for this one, if they're opposites, it makes a 1, and so it just set the bit from 0. Isn't that so cool? And now, if we have this number, 1, 1, 1, 0, 1, 0, and we exclusive OR by the same number, oops, 0, 1, 0, 0, 0, 0, look what happens. Again, we keep all the same bits from before, the 1, 0, 1, 0, Those are all preserved by exclusive OR. But this one now, because they're the same and exclusive OR doesn't give back true when they're the same, it gives back 0. Isn't that awesome? So you can exclusive OR by this special number to toggle the 4th bit, no matter what. And what's that special number? You toggle by, well, it's the number 1, and I want bit 4 set, so it's 1 left shifted by 4. X exclusive ORed with the number with just bit 4 set. That's 1 left shifted by 4. Okay? That's the answer, and that will make it work. So hopefully that was fun. There are, of course, more difficult ways to do this with just your ands and ors and things, but that will take more effort. This is kind of nice and clean. All right, so exclusive OR, that's another good thing that it's for. And maybe you discovered that as you were working on this. So I think that's everything that I wanted to talk about for these slides. I'm sad that I can't teach you programming paradigms, but feel free to read ahead. And that is everything that I wanted to talk about today. So I will see you next week.